shrink this one down a little bit just so I can get to where I can see the, oops, can only shrink so far. It's asking you, actually, this is, the notation that I prefer for this is to take f of h of x. Those mean the same thing. And that may help you a lot right there. Okay? So what it's saying is to take h of x, which is x plus 5 over 3, and put that in place of x in f of x. And since f of x is negative x, then this is negative that quantity minus 1. Okay? And then it says you're actually going to plug in the number 5, because you're going to use x equals 5, because this is what they actually gave you, was f of h of 5. So you're going to plug that in place of 5, negative parentheses 5 plus 5 over 3 minus 1 equals negative 10 over 3 minus 1. And use your calculator to finish that up. And since it started as a fraction, at this point we're going to keep it as a fraction, so we're going to go math and choose fraction, so our answer will come out in a fraction, and the answer is negative 13 over 3. Okay? And there may be quite a few of those, but this is the same process. And just remember that when you see two function letters with a little circle between them, that means the first one is the mama function. And you're going to use the baby function to put inside the parentheses. And it says that here you're reviewing your rational exponents. So again, over here on the side, I'll give you a little quick brush up before we go on. It says to take the cube root of the fifth root of x. And this is also a composition of functions. This is f of x is the cube root of x, and g of x is the fifth root of x, so this would be f of g of x. Okay, that's also, it's a composed function. But you have to remember your power rules, and your power rule says that the square root, or excuse me, the fifth root of x is the same as x to the 1 over 5 power. And the cube root of anything cube root of a flour is equal to the flour to the 1/3 power. Okay? That's just telling you how to do the powers. Your radicals are the same as fractional powers. And the numerator of the fraction is what the power is under the radical, and the denominator is what it is on the outside of the radical. So since you're actually taking the cube root of the 5th root, this is equivalent to saying x to the 1/5 power raised to the 1/3 power. And your rules for exponents say that that's equal to x to the 1 over 5 times 3 is 15th power. So if you're rusty on your rules for exponents, you're going to want to go brush up on those. And you are going to use these ideas a lot in in chapter 12. These are logarithm rules. Has anybody actually started this quiz yet? Anybody? But you haven't started it. Well, if you did, I can throw out the first attempt, and I think I'll probably throw that one out because after I looked at this.
There's others.
Okay, I'm going to throw out this question. I do expect you to know how to do that. I know it's complicated and ugly, but I will explain how to do one like that. What you really need to remember on this one, unfortunately it's hard to get it where you can see the whole thing, is that this is x over y minus y over x in a set of parentheses divided by what's below 1 over y plus 1 over x or whatever it is. So if you'll write it that way, and remember that when you have two different denominators, you got to get a common denominator. So then you get your numerator with a common denominator, your denominator with a common denominator, and then divide the numerator by the denominator, which means you flip the denominator over and then just multiply. And I will work this one out, and you do need to know how to do this, and there shouldn't be but one of those. You should actually be quite good at this point. This is another composition. It's exactly the same thing. What it's asking you is, what is the outside function? And since f comes first, it's on the outside, so it's f of x equals x squared. And then since it's g that's on the inside of the parentheses, then g is equal to 3 minus 7x. Remember, anytime it says f of g, whatever the variable is, f is the one that's on the outside, and g is the one that's on the inside. So f of x is equal to, those parentheses are being squared. So it's just the squaring function. G of x, on the other hand, is what's on the inside, 3 minus 7x. So that means g of x is 3 minus 7x. And what you're doing is what this function's doing is it's taking g of x and plugging it in for x in the f function. It's a function within a function. And you will see why when we get further into chapter 12, why you need to be able to understand these, and that these you do need to practice. You may need to do some of the homework problems to get those right. I think you can probably do that one pretty easily. This one I will throw out. And this is another rules for exponents problem. You've got to remember how to do your exponents. You would say 4k to the -1 is 4 to the 3rd times k to the -3, and then 2k to the -7 is 2 over k to the 7th. So go back and remember those rules for exponents. If you need to do the homework, it's there to get you some practice first.
We're actually locked out of the homework. We're locked out of the homework. You can't do, the way you got it set up right now, you can't do the homework.
Until you at least open and try the quiz, I know. And before I leave tonight, I'll go in and I'll delete those log problems because I didn't realize the log problems were still in there. I thought I took them out. Oops, no, I don't want to submit it yet. I want to look at one more. I'm going to be taking out number 10 too, because I can't think of a single place where you would actually have to factor anything that ugly. You may need to do this though, and I will try to post examples of the ones, but let me go ahead and see if I can fix this one and take out the ones that we don't want. Let me go back in there. It may not let me edit it. Yeah, it won't, because y'all have started it. I'll have to omit your assignment results, but I will go in and edit out those problems so that you'll be able to get the practice you really do need. And then I'll look in the homework too and see if they've included those log problems. You don't need those log problems at all. We won't use that in this chapter. Now you'll actually see as I get started tonight why it's going to be important that you be able to remember those rules for exponents. And you know, I was going to go in and actually do this through Nearpod, but I think I'm just going to actually go straight from the PowerPoint. And then I will set up a Nearpod for y'all to do between now and next week so that you can kind of review and get ahead a little bit.
Are those notes in D2L for chapter 12?
If there's not, I will get them loaded up. Yeah, usually it's good to have those in front of you while you're doing these. And the chapter 12 notes are, so you'll have them printed out next time because I printed them all out. There's 30 pages. But that includes your Shelby assignments.
Did you grade those this time? You didn't grade them, and that didn't help as far as
Yeah, when I got sick, I lost track of everything. I am so sorry, Tarina. And I have a student.
You're grading the test.
Yeah. Well, and you can retake this one. You can. I really feel bad for y'all because we lost that first class night because of the holiday, and yet the date was already set for us to take the test, and I was kind of stuck with having to go ahead and give you the test, even though I knew you weren't probably ready for it. And that's why, you know, if we need to retake one, you're going to get to retake this one. Come on, Mr. PowerPoint. There you go. Okay, what we're going to do now, after you've struggled with taking derivatives in chapter 11, hopefully this chapter will be easier. Because there are formulas to take derivatives. You don't always have to do this big long difference quotient or look at graphs and take limits. There are formulas to take derivatives. But you don't ever start out there, because if you don't understand what the derivative does, it doesn't help you know how to do one. So we do know the derivative is a tool for describing rate of change and velocity and the slope of a curve, but as we all also know, taking the derivative by using the definition can be difficult and tedious and annoying and just really frustrating. So we're going to take full advantage of the power of the derivative, but we need faster ways to calculate the derivative, one that doesn't require a half a page of algebra. So we're going to learn the faster method. One thing I want you to know up front is going to be that the notation for the derivative can be written any of these ways. Okay? This one, last one sort of makes the most sense because it's taking the derivative with respect to x of some function f of x. This is kind of the notation that the TI-84 calculator uses. This is called differential notation, and it's actually useful in a later chapter because it makes you able to remember a technique we're going to use later if you've got it actually as a fraction form. But this is my favorite notation. It's just f prime of x. If the derivative is f of x, f prime of x is the best way to express it. So the first rule we're going to have is called the constant rule, and on your notes pages, it's actually listed at the very top of the notes, and it says that if f of x is a constant, like f of x equals 10, or f of x equals pi, or f of x equals 2,012,000, if it's just a number, then the derivative is 0. Doesn't matter how big, how small that the constant is, regardless of what the constant is, the derivative of the constant is always 0. Which means if I was taking the derivative of f of x equals 6, then f prime is 0. Doesn't matter what x is. The derivative is 0. Okay? And the reason the rule makes sense, if you think about what does a constant function look like? What does f of x equals 6 look like? Visualize f of x. It's a horizontal line that goes through the point of 0, 6. So if x changes from -5 to -4, did the value of the function change? No. If it changes from -1 to +1, no. Because what's the slope of a horizontal line? 0. And the derivative is simply a formula for finding the slope of a function. And if you know the slope of a horizontal line is 0, then the derivative of a constant's got to be 0, because that's a horizontal line that you're finding the derivative of. And this is for visually oriented people like me, this is a graph that shows you why that's true. You know, y is a constant. P just simply, its y coordinate tells you what the value of k is. And it's a horizontal line through 0k. So if you take the derivative of any point on that line, doesn't matter, the 2 points are always going to be the same. The difference in the y values are always going to be 0. That means the slope is 0. So this is just kind of like driving the point home. If f of x is equal to 9, then f prime of x is equal to 0. If h of t is equal to pi, then dt of h of t is equal to 0. If y is equal to 2 to the third power, 2 to the third power is 8. It's still a constant even though there's a power there. So dy dx is equal to 0. Okay? That's always everybody's favorite rule because that's the one everybody can remember. We also have something called the derivative of a power function, meaning that x, the variable, whether it's x or t or p or whatever it is, the variable has a power on it, and the power is some number. The number does not have to be a whole number. And it is not restricted from being 0. But it does have a power. So if f of x is x, the power on that x is 1. And the derivative of that function f of x is 1. And the way that you do the power rule is you bring the power down in front of the variable and then subtract 1 from the power. So if this is f of x is x to the first, then you bring the 1 down in front of the x and then subtract 1 minus 1 and get 0. But what's x to the 0? 1. And 1 times 1 is still 1. Okay? If you have x squared, then you bring the square, the 2, down in front of the x, and then reduce the 2 by 1. 2 minus 1 is 1, so it's 2x to the first power, which is 2x. And again with 3, you bring the 3 down in front, 3x, to the 3 minus 1, which is 3x squared. And on with the fourth, you bring the 4 down in front, reduce the power by 1, and you get 4x to the third power. The way you remember the power rule is you drop it in front and reduce it by 1. You're dropping it to the front, reduce it by 1. Okay? If x is negative, nothing changes. If it is x to the negative 1 drops down in the front. You have negative 1x to the negative 1 minus 1 is x to the negative 2. So you have negative x to the negative 2 power. Now you can rewrite that as negative 1 over x squared, but I'm not going to make you do that. I have no problem, like, I know every algebra teacher you've ever had your whole entire life said, you can't have negative powers. Yes, you can. They work out just fine. Plug it into your calculator. Your calculator knows how to handle negative powers. So I'm not going to make you do all these little nitpicky things as long as you're going to get the right answer. I'm interested you to do the calculus. Your algebra only needs you to be able to do enough to get it into a form you can do the calculus on. And then, as I pointed out in the review part, x to the 1/2 power is the square root of x. But it still works the same. You drop the 1/2 power down in front. So 1/2 times x to the 1/2 minus 1 is negative 1/2 power. And I'm fine with that first form there. Or even if you have x to the negative 1/2 over 2, either one. You don't have to go to 1 over 2x to the 1/2 power. But the thing I want you to remember is that x to the 1/2 power is the same as the square root of x, because there is no rule for derivatives or square roots. So you have to know that you turn square root into a fractional power. Okay? That's why that's in the review. So this is your memory device. Drop and reduce. Drop it in front, reduce it down. And these are all in the notes that I've got for you. And if they're not in D2L, they will be before midnight tonight. So here's your example. And before I show you the answer, tell me, what do you think f prime of x is?
6x to the 5th.
Okay, 6x to the 5th. Does that make sense to everybody? Drop it, reduce it. Y is equal to t, and I'm just reminding you that that's t to the first. What's dy dt? Think carefully. Drop the 1 in front, reduce the power. 1. The variable drops out because it goes to a 0 power. What if it's y equals 1 over x to the third? Now, I don't have a rule for 1 over x to the third, but how could I make that into something where I have a power without it having to be in a denominator? That's right, it's x to the negative 3, so what's dy dt? Don't worry about simplifying it. Okay, negative 3x to the negative 4. Because you drop the negative 3 down in front, you convert it to x to the negative 3. And then drop the negative 3 down in front and then reduce the negative 3 by 1 more. Now, you can do this. I'm telling you up front, I know that works. But if you stopped here, I'm happy. This is algebra. That's calculus. Okay? I'm grading you on calculus, not algebra. What is the derivative of x to the 4/3? Drop it and reduce. I think he's right. Because 4/3 minus 1 is 1/3. So it's 4/3 x to the 4/3 minus 1, and since 4/3 minus 1 is 1/3, it's 4/3 times x to the 1/3 power. One more. And I went ahead and showed you the trick on this one. The square root of z is z to the 1/2. So you drop the 1/2 in front, and then the power becomes 1/2 minus 1, which leaves it at negative 1/2. And you can write it any of those 3 ways, but I want to see that one first. Because I know how you did the calculus at this point. After that, it's just algebra. Okay? Derivative of a constant times a function. Basically what all that says is what it says in English down here at the bottom. The derivative of a constant times a function is the constant times the derivative of the function. Just hold the constant out front and let it ride along. That's really what that means. Here your function is x to the 4th, but it's multiplied by 8. So keep the 8, just leave it sitting out there, and find the derivative of x to the 4th. What's the derivative of x to the 4th? 4x to the 3rd. Okay, 4x to the 3rd times 8. 32x to the 3rd. Okay? It still follows the power rule if you think about it. Take the power, drop it down in front of the whole thing. That way it'll multiply times the constant, and then reduce the power by 1. What about negative 3/4 to the 12th? That's right. Negative 3/4 times 12x to the 11th. Now, that was the calculus. You already did the calculus. If you carry it another step, it might look a little bit better. Negative 3/4 times 12 is negative 9, and you can do that on your calculator if you want to, so you don't mess it up. Because believe me, I know all about messing it up. Y'all saw the test I did tonight. What's the derivative of negative 8t? Negative 8, because the t disappears. Its power was 1, so it disappears. (10p to the 2/3 or 3/2 power.
It's 15p half.
Okay. That's good. You did the calculus, reduced it in your head. Because it's 3/2 times 10p to the 1/2 power. And 10 times 3/2 is 15. Okay? Is this better than chapter 11? Everybody's usually saying, mm-hmm. This kind of makes some sense. It's just using some formula. What if you got y equals 6 over x? What can we do with that x? We don't have a rule for x's in the denominator. What we got to do? Make it a negative exponent and move it to the numerator. So 6x to the negative 1, and then that means it's negative 1 times 6x to the negative 2. This is called the sum and difference rule. And basically, in a nutshell, what it says is if you've got a bunch of different terms added and subtracted together, take the derivative of each term separately by itself and add or subtract them together. The rules look worse than doing the problems do. If you got two terms, 6x to the third and 15x squared, and they're being added together, take the derivative of 6x to the third and get 18x squared, and take the derivative of 15x squared and get, and then you add those two together. Now, the explanation uses something called a substitution, and that substitution might be kind of helpful later on when we do something called chain rule. But if you do it the way we just talked through it, it really works just as well. So you can kind of skip that and say, okay, if y is 6x to the third plus 15x squared, then y prime, or dy dx, or whatever you want to call it, is 18x squared plus 2 times 15 is 30, x to the first. So you don't have to actually do the u and the v stuff that it shows there. Same thing. What's the derivative of the first term? Y'all give David a break and help him out.
48.
Okay, 48 to the third. Minus, how are you going to handle 6 square root of t? Change it to t to the 1/2. So the derivative of 6 times the square root of t is, okay, 3t to the negative half. And what are you going to do with that 5 over t? Okay, which makes its derivative. Negative 1 times 5 is, okay, and then since it's t to the minus 1, you got to reduce it. Minus 1 is, oh, negative 2. Yeah, you're okay. Yeah, you've had a test. You deserve a break. So good job. Now, this is the answer that I want to see on your paper. Okay? This is the answer you can put on your paper and I will accept it, but this is extra work that doesn't get you any brownie points.
But it will be part on that, but
No, actually, we have determined that it is not. We first thought that it was, and actually I think it may originally have been the first time I taught this course a couple, 3 years ago. Actually, it's not the first time I taught it. It was the first time I came back to teaching it with my math lab. And they were putting in their answers because I told them it should work, and they were coming back and saying, no, it wants the whole drawn out bloody algebra thing. So I kind of raised a little bit of Cain with the Pearson people and said, this is ridiculous. Your programmers can't enjoy programming that much algebra. Make it accept the first answer. And now it does. So if you put...
In some cases, I noticed I think it was Jack Crossfield quiz, it'll say it in like a blue letter, but it'll say use only positive exponents.
Yeah.
Or whatever.
Yeah, and the reason for that is because that is being programmed by people that did the algebra review, and that's what algebra teachers jumped up and down about, you know, that you only have to have positive exponents. So it's coming from that. But when you get to calculus, people that are teaching calculus really could care less if you use only positive exponents, because they know that it works just as well with negative exponents. So at least they did listen to the calculus part. So in the My Math Lab for Chapter 12, not the skills review, but the actual Chapter 12 homework, it should take your first answer. And if it doesn't, and you determine that you're right, or you think you're right, all you gotta do is click Ask My Instructor, or shoot me a message or mine and say, would you please look at this when it's telling me it's wrong? And if I decide it's right, I'm gonna give you credit. Because I trump My Math Lab. Okay, now this one's ugly. I'm gonna tell you that up front, folks. This is ugly. There's 2 or 3 different ways you can do this problem. But the way that works best, and I'm gonna go ahead and show you the solution without asking you to help me with it, is to break it up and put the x under each part of the numerator. Okay? X cubed over x and 3 square root of x over x. And then change that square root to a 1/2 power, because you know that you have to have it as a 1/2 power. And then your rules for exponents, remember I told you in your skills review, you need to remember how to do those exponents. Those rules for exponents say that x to the 1/2 over x means you say 1/2 minus 1. And 1/2 minus 1 is negative 1/2. And that 3 stays in the numerator, and so does the x. And from there on, the derivative of x squared is 2x. And the derivative of 3x to the negative 1/2 is negative 1/2 times 3 times x to the negative 3/2. And if you want to call that negative 3/2 x, that's fine. You probably actually should do that. So you do need to go as far as that step, but I don't care if you go to that one. I just know that it's going to show you both of those when you, if you read the textbook at all. Now, does anybody have any questions on that one? That one's got a lot of algebra review in it. You never know how much you really did need some of your algebra skills until you get to calculus. But some of the skills that they drilled into you weren't the ones that you really needed. Yeah. You need to know how to convert rational expressions to fractional exponent expressions. Okay, now this one on the surface, you look at it and you think, I don't know how to do that. Because this is one of those composition of functions. This is a function, actually it's the difference between 2 functions being squared. But the way that we're going to handle that, because we don't have a rule right now to handle that, we have another rule later that we can use. But we haven't learned that other rule yet, so we've got to make it into something we can do now. And all we've got now is a power rule and a sum and difference rule. So what we're going to do first is we're going to rewrite f of x by actually squaring that expression and getting 16x to the 4th minus 24x to the 3rd plus 9x squared. Then all you have to do is take the derivative of each term. So 3 times 64x to the 2nd, and 2 times 72x to the 1st, and 18x to the 0 becomes 18. Okay? Oh, I'm sorry. I stood right there and told you to take the derivative of the derivative. 4 times 16 is 64x to the 3rd, and 3 times negative 24 is negative 72x squared, and 2 times 9 is 18x. Okay? So again, just taking the derivative of each term and adding and subtracting is whatever the function tells you to do. Now, this is going to be the first place that I'm going to point out to you that your calculator will be helpful. You can use it to verify that the derivative you get by doing the calculus by hand is correct. What you do is you go and you actually enter in the original function, 6x to the third plus 15x squared, or, well, it would have helped if I had actually gotten that one right. Hang on. I've got them mixed up there, so I need to fix something. That's supposed to be a plus. Which means this is going to be a plus. Okay, here's your function. 6x to the third plus 15x squared. 3 times 6 is 18x squared. 2 times 15 is 30x. So this is your derivative. But you're still new at this. You want to see if you did it right. Here's one way you can do it. Go to your calculator and enter the original function. 6x to the third plus 15x squared in y1. This actually turns out to be really handy, especially if it's a really ugly expression. Stop that. And then go down, and the way you get this in deriv is you press your math key and go down to number 8. Your function is in y1, so you hit your vars key, go to your y vars key and choose function and then choose y1. And then a comma, and then x, and then a comma, and then another x. Now you can do this with a number on the home screen and it'll find the derivative at a particular value of x. This is saying, draw me a graph of the derivative of that function. Let x be whatever x wants to be. Now, if you have a TI-84, you have to enter the x first, then y1, and then an x at the other end. The order of entering them is a little bit different. And then, in order to check your work, what you want to do is you want to enter in what you thought the answer was. And since I'm not really interested in looking at the graph of the original function, I really could care less, then I'm going to put my cursor on it and turn it off, which you notice here this one's turned off. So I'm going to see if I graph these two, do they appear to be the same function, or will I see two different lines? If I see two different lines, I did something wrong when I got my derivative. But if I only see one line or one curve, that means my answer matches the numerical derivative answer, which means my answer is right. And I set my window up to go from -5 to 5 just because all the good stuff happens there. You could just go zoom 6 too. So what I see there is it's still graphing, but there's no more graph coming up. And then just to be sure that, you know, it just didn't accidentally look too close there, I usually go zoom 0 to do the zoom fit screen. And it's still graphing. So even if I zoom out, I'm still seeing pretty much that it looks the same. I'm only seeing one line. Okay? So I feel pretty good that I did the calculus right. So having your calculator can be very handy. And that's the graph that I was showing you there. The other thing you can do is you can actually go and pick out a point on it, or you can just trace. Just trace on it. Right now it says, well, this is on the numerical derivative, but if you press your down arrow key, this says this is your formula. And notice that the points didn't change just because I'm jumping back and forth between them. It doesn't matter where I am, the y values stay the same regardless of which function I'm on. So the last example here says, suppose that the total cost in hundreds of dollars to produce X thousand barrels of a beverage is given by C of X is equal to 4x squared plus 100x plus 500. Find the marginal cost for the following values of X. Well, the marginal cost is simply the derivative of C of X because it's the rate of change of cost. So you take the derivative, and the derivative is 8x plus 100. And then you plug in 5. And C prime of 5 is 8 times 5 plus 100, which is 140. And the important thing here is not just that you be able to do that, but you be able to tell me what that means. Because you are going into business, you are going to need to be able to discuss what these things mean in context. And what this means is after 5,000 barrels of the beverage have been produced, the cost to produce another barrel, another 1,000 barrels, will be approximately $100, which makes it $14,000. Okay? You need to put it back in context with the right units. So you've made 5,000 barrels, you're going to make another 1,000. And the cost of that additional 1,000 barrels is going to be $14,000. The actual cost to produce 1,000 more barrels is C of 6 minus C of 5, so you go back to the original function. So the actual cost to produce 1,000 more barrels is, again, $14,400 or $14,400. That's not the rate of change. That's the actual cost of that additional 1,000 barrels.
What's the advantage of knowing the marginal cost?
That's the rate at which your cost is increasing at that point for the next 1,000 barrels. Okay?
How does that go?
Well, if you go back to what we looked at,
Actual cost.
if you go back to what we looked at that point the actual and the marginal cost are pretty close to the same, but actually the marginal cost makes it appear that the actual cost is less than what it is. But you know that it is going up by approximately what the marginal cost says that it is. And the thing that happens is the further along you go, the more and more thousands of barrels you produce, that marginal cost reduces down. And it also, the cost of actually producing that next 1,000 reduces down up to a point. Now you are going to hit a place where if you produce another 1,000, the cost is actually not ever going to continue increasing. It's going to kind of flatten out, or else if it does continue increasing, you're probably going to start losing money because your revenue is going to outweigh it. But if there's a relationship between the marginal cost and the average cost. And that the marginal cost is, it is increasing by about $14,000. The actual cost of that 1,000 is saying, well, it actually was a little more than 14,000, it's 14,400. But that difference between your marginal and your actual get very small as your number of units that you manufacture are increasing, depending on the function. Now, this one, it's got an almost linear rate of change, which means the rate of change is pretty constant. It's, you know, the 8 times x, once you let x get above 10, it kind of takes over the little bit that the 100 changes it. So as x increases, your derivative here is going to mostly be influenced by the fact it's going to cost you $800 for every extra $1,000. And that's where that error's coming in from, is that constant, your fixed cost. If you think about it, as you produce more and more, your marginal cost starts counting more in your total cost than your fixed cost does. Because your fixed cost is actually being spread out over more and more units. If your fixed cost is $100 and it's spread out over 100 units, that's $1 a piece. But if it's $100 spread out over 1,000 units, then that's considerably less. So that's the source of that extra 440 when x is relatively small. When x is large, that 100 doesn't have much influence. And looking here again, I think this is going to kind of bear out what we're talking about. Suppose the total cost in hundreds of dollars to produce the 1,000 barrels is 4x squared plus 100x plus 500. Find the marginal cost for x equals 30. Well, the derivative is still the same as it was before. But if you plug 30 into the derivative, you get 340, which is 340 hundredths, so that's $34,000. So if you've already produced 30, it's going to cost you $34,000 to produce an additional 1,000 barrels of the beverage. And that's increased by about $20,000 at a production level of $30,000 compared, or excuse me, 30,000 barrels when you compare it to only 5,000 barrels. So what that's telling you is that your marginal cost is eating you up at that point. So you better be hoping the revenue balances it out. This is the part of the chapter that people usually find to be the toughest, because people have a hard time thinking about demand functions. And after talking with students about this for a while, my own experience is the same as theirs. The problem with doing demand functions is when you look at it, it looks like there's too darn many variables. You've got R's and D's and Q's and P's, and you're wondering how in the heck all these things are supposed to mush together, because everything else we've done up to there, there's two variables, X and Y. So we're going to go carefully on this. We did talk about it some in the last section, but we do need to deal with demand functions because you are business majors and some of you are economics majors. So the total revenue, which is R of Q, and the best way to keep in mind in your brain what these different things represent, P always represents price per unit. Okay? It's a price. Price determines both supply and demand. Demand goes up as the price increases. Demand goes down as the price increases, but supply goes up as the price increases. So there's only one variable in supply and demand. But the other variable actually in both of them is in quantity, and Q represents the quantity. So it is the price per quantity. that you need to worry about. So the price is equal to the demand at a particular quantity. It's basically what the consumers are willing to purchase if they have to buy something and it costs them P dollars. Demand functions also lead into revenue functions. The total revenue for the company from selling those Q100 units is related to the price also. And revenue is the quantity produced times the price for each unit. Okay? And since P is dependent upon the demand, or determines the demand, then it's Q times D of Q. Quantity times what price can you have at that quantity. So for example here, the demand function is given by price is equal to $50,000 minus Q, the number of units produced, divided by $25,000. And that only holds for Q being between $0 and $50,000. Because obviously, you don't have negative quantity and you don't have negative price. So we want to find the marginal revenue when Q is 10,000 units. Now we've got a lot of things going on here. We've got to think about demand and price and quantities, but we also have to think about marginal, meaning we have to take the derivative of what we see up there. We have to take the derivative of P at some point. First thing we want to do though is we really need the function for revenue. So the revenue for a certain quantity is that quantity times the price, which determines the demand. And since the price is 50,000 minus Q over 25,000, if you multiply your numerator here, this is Q times the price, quantity times price to get revenue. 50,000 times Q is 50,000 Q, and Q times Q is Q squared over 25,000. And then using the same little trick we used earlier, you're going to break up that 25,000 and put it under the first term in the numerator. And then also put it under the second term in the numerator. So 50,000 Q over 25,000 is 2Q. And Q squared over 25,000 is, we're going to leave that as 1 over 25,000 times Q squared. Because that way we can think of 1 over 25,000 as just being coefficient. So when you take the derivative, I'm going to go back and forth here for a second. If you take the derivative of 2Q, what do you get? 2. When you take the derivative of 1 over 2,500, or 25,000 times Q squared, what happens? You get 2 times that fraction times Q. And 2 times 1 over 25,000 turns into 2 over 25,000. You don't even have to reduce that. It's not necessary. The arithmetic teacher can just be mad all she wants to. You can take 2 over 25,000 and plug in that Q is supposed to be $10,000 and it works out just fine. So the marginal revenue is 2 minus 2 over 25,000 times 10,000, which is just 1.2. And that is $1.2, so $1.20 per unit. And what that means, the next item sold when you've made, after you've sold 10,000 units, you're going to get an additional revenue off the next one of $1.20. Okay? And this graph shows the demand function and the marginal revenue function. And notice that when Q is equal to 10,000 right here, When Q is equal to 10,000, the demand is the demand price is $1.60. So people are willing to pay $1.60 for it to get 10,000 units of it sold. But the marginal revenue is $1.20 per unit. Okay? And notice that as you have more and more quantity, for example, here I'm saying we're at about 25,000, then the additional revenue pretty much says, nope, you're not getting any more. While your price is still, if you look at it, only a little less than $1.20 per unit. And then the last part of this is the actual revenue function. This is R of Q, which is P times Q. And what you look at here is that when Q is $10,000, the revenue is $16,000, but it's increasing by $1.20 per additional item. Keep in mind that $1.20 per additional item, that this is $10,000 on that graph. The interesting thing this shows you is that your revenue, and again, this is the revenue function, not the marginal revenue, your revenue actually hits a peak. You're not going to ever make more than $25,000 on this. And what we'll learn in the future is that if you took the derivative at whatever that point is, which is $25,000, your marginal revenue at that point will be zero. And that's because your revenue flattens out. And if you tried to take your revenue at any point after that, what's happening is your revenue's falling. Your revenue's actually falling after that. The economists usually give demand function as the independent variable, the way we just looked at it. But it might make more sense for some of you to think of it as a demand as a function of price. So if the demand for the function is Q is 50,000 minus 25,000 P, then P is the price in dollars, as long as P is between 0 and 2. So apparently this is not a terribly expensive item. And find the marginal revenue when the price is $1.60. And what you do there is you basically just take the derivative of Q. Well, actually, you solve it for P and you get this expression. And you wind up with the exact same thing we did before. Okay? Marginal profit works kind of the same way. So suppose that the cost function for that product is given by C of Q is 2100 plus 0.25 Q. Find the marginal profit when you have 1,500 units. First thing you have to do is you have to take cost and subtract it from the revenue. So when we take the cost and revenue and subtract them, there's where your algebra skills come into play again. You wind up with that the profit for Q quantity is 1.75 times Q minus 1 over 2,500 Q squared minus 2,100. And at 1,500, that's going to be 55 cents per unit. So your profit is increasing by 55 cents per unit when you make 15,000 units. And if you increase that to 21,875 units, your profit is increasing by nothing. It's gone flat. You're not losing money, but you've reached your maximum profit. And if you make 25,000 units, you are now losing money. You are losing profit at the rate of 25 cents per unit. So what we're looking at here is if you sell more than 21,875 units, your profit becomes negative, and that indicates production beyond that level is going to reduce your profit, and that would be a good thing to know, is when should you stop producing anymore? When have you maxed out your profitability? And this is just a graphic representation of the same thing. And I'll leave that, let you analyze those and ask me questions if you have them. You have your turns, and basically try to get your 12.1 show me homework done. See if you can get it done by Friday. If you can't get it done by Friday, do it as quick as you can, but I'd like to see it before next week. Even if you think it's wrong, you know, give it your best shot. The show me homework is not that big long problem I gave you at the end. There may be a reference to it. In fact, I think there is. Let me look. No, there's not. The your turn problems are just straight applying your power rule, so you're okay. You don't have to do any applications for show me. Okay? And I know I wore your brain out tonight giving you a test and making you cover new material, but hopefully it'll keep us on track for next time.